Number 1. Now, you might look at this and say, that doesn't feel like the first thing that we've learned. So let me tell you something else about the test. The test is not in order of the material that you learned. So in other words, we're going to jump around. So don't think it's like, oh, the first part of the test, I need to use things I learned from the first part of the class. The last part of the test, I need from the last part of the class. We will jump around. So let's take a look at this problem. Find y of x given that y prime is equal to 2y squared e to the 2x. And one of the things that we have to learn, and this is probably one of the hardest things about these tests, is figuring out, what are we doing? What's the problem here? What type of thing is this? So looking at this problem here, what I see here is I see a y prime and a 2y squared. So whenever I see an equation that involves the derivative and the original function, this is called a differential equation. And so in particular, this is the very last topic that we learned. So this is a separable differential equation. So for separable differential equation, there's 3 steps. There's the separable, tells us that the first step is to separate. The second step is to integrate. Does anyone remember the third step? Uncomplicate, that is correct. Now you might say, that's not a real word, but that's okay. The idea is good enough. So we're going to start y prime equals 2y squared e to the 2x. I'm going to bring the y squared across. So y prime over y squared equals 2 e to the 2x. Now sometimes the way we do this is instead of thinking of y prime as y prime, we think of it as dy over dx. And we say, this should really be dy over y squared equals 2 e to the 2x dx. And both ways are done depending upon how you've seen it. Both are fine. Now when you do it with the d notation, it really makes sense as to what's going to happen. Now what we're going to do is we're going to go to step 2, which is to integrate. So we integrate both sides, find the antiderivative. And so dy over y squared, that's really y to the minus 2 dy. And so that's still 2e to the 2x over here. And so the integral of y to the minus 2, now that's something to a power. I add 1, and I divide by the new power, which is the same as multiplying by a minus. And then that's going to be equal to the integral of 2e to the 2x. Well, that's 2e to the 2x. And I divide by 2, and I add plus c. I only need 1 plus c. I don't need to have a plus c on both sides. And now I say, okay, what do I have? Well, minus 1 over y equals e to the 2x plus c. And we come back to say, well, we have to figure out the plus c. So this is where we're into our uncomplicate phase. Now in this case, we're trying to find the function y, so I have to solve for y. So I can either find c first and then find y, or I can find y and then find c. It just feels, what's easier to do. Now in this case, it's pretty straightforward to find c right away. So y of 0 equals 1 means that when I plug in x equals 0, so this is what I'm plugging in, so this is my x, I get an output of y as 1. So everywhere where I see y becomes 1, and everywhere where I see x, it becomes 0. So minus 1 over 1 is equal to e to the 0 plus c. Well, minus 1 over 1 is minus 1. E to the 0 is plus 1, but it's on the other side, so I have to bring it across. So I say, aha, c is really minus 2. All right, so updating. Minus 1 over y is equal to e to the 2x minus 2. I'll multiply both sides by a minus, because I don't like that minus there. 1 over y is equal to 2 minus e to the 2x. And now I can flip both sides. Because when it says solve for y, find y, it says literally I want to get down to a single y. So flipping, we get y is equal to 1 over 2 minus e to the 2x. And we're done, because we found y. It's right there. 1 over 2 minus e to the 2x. Okay, so if you see a separable differential equation, just remember, separate, integrate, uncomplicate. Now, sometimes they'll have you do different things. So look at your quiz problems from quiz 12. There are some examples of things that you might do with separable differential equations. All right. Number 2. Find the limit as x approaches 0 of the quantity 1 over x cubed, the integral from 0 to x, sine of t squared dt. Now this gets us back to the first part of the course, limits. But we have a new friend we can bring along for the ride. Do you remember who our new friend is? L'hôpital. Oh, l'hôpital. So, if you see the word limit, and it doesn't say you can't use l'hôpital, we can use l'hôpital. Now, you might say, well, why are you bringing this point up? Well, this 1 over x cubed, integral from 0 to x, sine of t squared, another way it could have been written is that this is the limit as x goes to 0 of a fraction. Downstairs being the x cubed, upstairs being the integral from 0 to x, sine of t squared dt. All right, so that's what we have. Now, if you look at this, it's a ratio, and in the denominator, because we're letting x go to 0, x cubed, well, that goes to 0. That's not a surprise. What about the integral from 0 to x sine of t squared? Well, it goes 0 to 0. What's the integral from 0 to 0? It's 0. Yeah, if you integrate from somewhere to the same somewhere, it's always 0. So this is going to 0 over 0. Aha! L'hôpital. Okay, so l'hôpital says I can take the derivative. Now you've got to remember how to apply it. Limit, x goes to 0. Downstairs, take the derivative, 3x squared. This isn't a quotient rule. You're taking the derivative separately at the top and bottom. Upstairs, well, what is that? We have the derivative of the integral, 0 to x, sine of t squared, dt. Is there something that allows us to find this integral? Something very fun. Yeah, the fundamental theorem. So, this in fact is really tailor-made for the fundamental theorem. Integral from a value to x, sine of t squared. Well, what happens is this is my sine of t squared, that's like my f of t. And the fundamental theorem says, because this is simply x, I get f of x. So that's sine of x squared. All right, well, where does this go to? I still get 0 downstairs. What do I get upstairs? I'll get sine of 0. Sine of 0 is? It's 0. Ah, 0 over 0. Oh, l'hôpital, mon ami. Yet again. Okay, limit. X goes to 0. Downstairs, what do we have? 6x. Upstairs, well, what do we do? Derivative of sine is cosine. Inside, x squared times the derivative of the inside, which is 2x. And what does this go to? Well, it goes to 0 over 0. But wait a second, we can be smart here. Remember, you're smart people. And smart people always look for algebra and maybe a little bit of trig on the side. What do you see here? What's the algebra thing we can do? We can cancel out some 2x's. So, I can cancel an x. I can even divide the 2 into 6 and say, really, this is the limit as x goes to 0 of cosine of x squared over 3. Well, now we know game over. Whatever happens, happens now. Because the denominator isn't going to 0. It isn't going to infinity. It's going to something nice. What does this go to? Well, upstairs, cosine of 0 squared, 1. Downstairs, 3 becomes 3. 1/3. That's our limit. All right. Two down, 3 coming up next. For the following function, f of x is the log of the absolute value of x plus 3 over x to the fourth. Determine the intervals for when the function is concave up and when it is concave down. So, when you see concavity, what derivative do we need to be looking at? We need to look at the second derivative. Concavity is all about the second derivative. So I need to take two derivatives. Now, there's two choices here. One is to do the second derivative painfully. The other one is to do it gently. Now you're probably thinking, I want the gentle one. What's the gentle one? Tell me more. Well, the gentle one is to say, look, don't rush into taking your derivative. Think about what you have. I have a log, and log has magical, wonderful properties. In particular, there's two properties, well, really three. Log of division becomes subtraction, addition becomes multiplication, and then exponents can come down. Those are the three. So whenever you have a log involved, it's good to know about properties of logs. And this is a case when it pays to wait to take your derivative. So I can write it as log of x plus 3 minus log of x to the fourth. But I can go one step further and say this is really log of x plus 3 minus 4 log x. And in this case, now it's going to be much easier to take the derivative. There's no quotient rule involved. It's very straightforward. So let's go ahead and do that. All right, so here we go. We rewrote f of x. We said that was log of x plus 3 minus 4 log x. So f prime of x is 1 over x plus 3, and then minus 4 times 1 over x. Now that's just the first derivative. Note, by the way, if you want, you could have written this as x plus 3 to the minus 1 minus 4x to the minus 1. Second derivative. And this is the reason why I chose to rewrite it this way, because 1 over x plus 3 is actually not very hard to take a derivative, but you might be tempted to do a quotient rule. It's actually easier to do a chain rule. So minus 1 x plus 3 to the minus 2 times root of the inside, which is 1. Then minus 4 minus 1 x to the minus 2. So we have our second derivative, minus 1 over x plus 3 squared plus 4 over x squared. All right, so that's our second derivative. Now, to figure out concavity, I have to understand something about the second derivative. I need to know, essentially, when it's positive and when it's negative. Now, in order to do that, I take a look and say, well, where can I switch signs? So there are two things I have to be on the lookout for. When is the second derivative 0, and when is the second derivative undefined? Both of these are things I have to pay attention to. And the reason I bring up the second derivative being undefined is I do have things in the denominator. So if I ever have something in the denominator, I always have to check. Could this be undefined? Well, I suspect it could be. I strongly suspect it could be, actually, given that there's an x. All right. Well, to do the next thing, I'm going to add these together. So common denominator would be x squared times x plus 3 squared. So that would be minus x squared divided by x plus 3 squared plus 4 times x plus 3 squared. Oops, and then I forgot my x squared here. And then it would be x squared, x plus 3 squared. Okay, so I'm going to bring it up over here. So what do we have? We have upstairs minus x squared plus 4 times x squared plus 6x plus 9. It's making me a little nervous. Well, we'll see what happens. X squared, s plus 3 squared. All right. Well, let's see, what do we get? That becomes minus x squared plus 4x squared becomes 3x squared, then plus 24x plus 36. So I multiplied the 4 through, and I subtracted the x squared off. Now, to really go all the way, I really need to understand the top. So to help me understand the top, I'm going to start by factoring the 3 out. That's x squared plus 8x plus 12, if I do that right, divided by x squared, x plus 3 squared. Now, does x squared plus 8x plus 12, does that factor in a nice way? I mean, if we're lucky, it'll factor. Have we been lucky? It does factor. Wow, it's almost as if this class is going to leave us with an unreasonable belief that everything factors, because it's very unreasonable to believe that. But that's okay. We'll take it for now. Okay, so here we go. X plus 2 up top, x plus 6 on top, x squared, x plus 3 squared. Now, we're almost ready. So, to finish it off, what do we need? We draw our number line, and let's talk about what points matter. Well, downstairs, I see a 0, and I see negative 3. Upstairs, what do I see? X plus 2, well, that'll be 0 at negative 2, and x plus 6 will be 0 at negative 6. So what I've done here is I've drawn myself a number line, and I said, all right, here's my number line. These are the places where I could potentially switch sign. Now, it doesn't mean I do switch sign, but I could potentially switch sign at those places. What do I do next to help me finish this up? So, next thing is plug stuff in. And you just go through one at a time. So plug something bigger than 0. Say a billion or 1. They both work. Okay. And if you plug it in, you'll see everything here is positive. Life is good. So second derivative is positive on that interval. Between 0 and negative 2, well, I could plug in negative 1. You'll see negative 1 plus 2 is positive. Negative 1 plus 6 is positive. Negative 1 squared is positive. 2 squared is positive. So still positive. All right. What about between negative 2 and negative 3? Well, negative 2.5. Now you'll notice, by the way, I didn't say what the value was. I just cared about the sign. Concave up, concave down. All you need is the sign. You don't need to know, whether it's positive 4 or positive 400. I don't care. I just care about the positive, not the 4 or the 400. Between negative 2 and negative 3, am I positive or negative? Well, here I actually do switch sign, because if, say, negative 2.5, you'll see that the x plus 2 term is now negative. If I go negative 4, the x plus 2 term is still negative. X plus 6 is positive. The downstairs, because of the squaring, is always positive. So here, I am still negative. And what if I'm below negative 6? What happens? Well, the answer is I'm now positive, because, say, negative 7. I'll get a negative and a negative. That makes it positive. Now, looking at this, it seems like our answer should have 3 pieces. Below negative 6, between negative 6 and negative 2, and above negative 2. However, there's a caveat here. This function is not defined for all x. So you really have to say, look, there's really a break at 3, and there's a break at 0. So, concave up. What's the answer? Well, below negative 6, and then between negative 2 and 0, and above 0. Concave down, what do we have? Well, between negative 6 and 3, and between negative 6 and negative 3, and whoops, there is a negative there, it's just hard to see that. Okay, maybe I should. Negative 6 less than x less than negative 3, and between negative 3 and negative 2. Again, you really can't combine these two together because the function breaks at negative 3. So that's it. Those are the answers when it's concave up and concave down. All right. I've been going for a while. How you doing? Any questions? It's a good time to pause. Don't feel the need to I can't ask a question. You can shout out a question.
How do you know it breaks at negative 3?
I know. Well, how do I know it breaks? Well, because look at the function. Log is undefined at 0. And so anything when I plug in log and I get a 0 involved, that's going to break the function. There's an asymptote involved. All right. This one, it's a good preview for what you're going to be doing in a few weeks when you show up to Calc 2. So you have a volume which is formed by spinning the region between y equals f of x and the x-axis, where a less than or equal to x less than or equal to b, and it's given by the following formula. So we're just taking this is not anything other than, here's a definition. It's 2 pi integral a to b of x f of x. Now, why is this true? You'll learn it in Calc 2. But for right now, it's just saying, here's a definition. Can you understand what it's saying? So the question then says, well, let's find a value, d greater than 0, so that the volume formed by spinning the region between y equals x to the d minus x to the 2d and the x-axis for 0 less than or equal to x less than or equal to 1 is maximal. Now here, it takes a while to think about it, but the question is, what type of problem are we doing? So, that's my question. What type of problem have we just found ourselves engaged in? I'll give you a hint. This word is important. It's an optimization problem. So, because we're trying to find something that's maximal. So, when we're looking for something which is maximal, that means we're engaging ourselves in an optimization type problem. So, when you're doing an optimization problem, the first thing you have to do is say, what am I optimizing? Well, what I'm optimizing is the volume. So what I have to do is come up with an expression for the volume in terms of what I'm trying to choose. And in particular, here's the key. Determine the value of d. So we've got to find this d. So what I'm going to do is I'm going to say, okay, let's find the volume. So the volume, according to the formula, 2 pi integral, and here a and b are 0 and 1, 0 and 1. And then I have x, and my f of x, that's this equation, x to the d minus x to 2d. And now, all of a sudden, we're like, wait a second, you said this was an optimization problem. When did it become an integration problem? See, isn't this fun? This is how we can tie things together. Math is fun like this. Okay, well, let's just carry this out. So we have 2 pi integral 0 to 1, x to the power d plus 1 minus x to the power 2 times d plus 1 dx. And you'll notice that this type of integration is one of our favorites, x to a power. We like x to a power. So when I integrate, I'm going to add 1 to the exponent. So in the first case, it'll be d plus 2. And then I divide by d plus 2. And in the second case, I'll add 1 to the exponent and get 2d plus 2 divided by 2d plus 2 and evaluate from 0 to 1. Now, we had a similar problem like this on an old exam. And it turned out that students got stuck at the next step. We didn't anticipate this. The next step is to evaluate at the endpoints. Now, when you evaluate at 0, not very big surprise, you get 0. Because it's 0 to a power. But here's where people got stuck. When you evaluate at 1, what is 1 to the power d plus 2? It's 1. If you take 1, raise it to any power, you get 1. So what is 1 to the power 2d plus 2? It's also 1. So this becomes 2 pi times 1 over d plus 2 minus 1 over 2d plus 2. Because this is what you get when you plug in 1, and when you plug in 0, it goes away. All right. So this is the volume. So this part right here, this is what we're trying to optimize. So we want to optimize this expression. Well, now that we know what we're trying to optimize, what do we do to it? When you're doing an optimization problem, step 1, find a formula for what you're trying to optimize in the variable you want to optimize with. That's what we've just done. What's step 2? So what? Take a derivative. Take a derivative. So optimization, set it up as a function of one variable. Sometimes you have to use information to get to 1. Take a derivative. And don't worry, we'll be doing more optimization problems we have 3 on these practice problems. Okay, so let's call this for a moment, well, we don't really need to call it anything. We call it v of d, just to emphasize it's a function of d. So v prime of d is 2 pi. Then 1 over d plus 2. Again, I can think of this as d plus 2 to the negative 1. So that becomes minus 1 over d plus 2 to the second power. And again, how did I get that? You can think of 1 over d plus 2 as d plus 2 to the minus 1. Then the next one, 1 over 2d plus 2 will become plus 2 divided by 2d plus 2 squared. Okay, so that was the chain rule, take the derivatives. All right, you've taken a derivative. What do you do next? Set it equal to 0. Optimization. Set up your formula, take a derivative, set it equal to 0, grab your answer. Okay, equals 0. Now the 2 pi doesn't matter because we can just divide out. So I have that the inside part equals to 0, which says I really need 2 divided by 2 times d plus 2 quantity squared is equal to 1 divided by d plus 2 quantity squared. And then I can do what's called cross multiply. So 2 times d plus 2 squared is equal to 2d plus 2 squared. Okay, so now it's just patient. 2d squared plus 4d plus 4, that's what you get if you square that, is equal to, here if you square it, you get 4d squared plus 8d plus 4. Okay, so, we'll expand, 2d squared plus 8d plus 8 equals 4d squared plus 8d plus 4. And now we're like, aha, this is very convenient. The 8d's are going to cancel out. Well, of course, that's very faint, so you can't see it. But imagine that I had picked a pen that was darker so that they canceled. There you go. And now we've moved stuff around. And so, for example, I can move the 2d squared across. I can move the 4 across. And if I do that, 4d squared minus 2d squared says 2d squared. And over here equals 4. D squared equals 2. So D becomes square root of 2. Now you might have said, wait a second, what about plus minus? Well, why do we know it's not plus minus? Because it tells us, take the positive one. Be positive. Now, is this our answer? You always have to be careful with optimization problems, because the optimization problems usually say you have to optimize and then you have to find something. Well, sometimes it'll say find the parameter, or sometimes it'll say, well, find the value. So, for example, find the volume. Or sometimes it'll say something else. In our case, it said determine D. So D is the answer, and so we're done. D equals square root of 2. Ah, fun problem. Good times. All right. Number 5. So this one is about antiderivatives. Find the antiderivative, or the indefinite integral, of the following expression. Sine of theta over cosine squared theta plus 1 minus sine of 2 theta over cosine squared theta plus 1. And it says make sure to indicate any substitutions made. So in other words, don't just write down an answer. We want to make sure you know the process. Now whenever you see addition and subtraction here, oftentimes it's a good idea to say, well, let me use the addition and subtraction, and let me think about it in pieces. Sine theta, cosine squared theta, plus 1 d theta, then minus sine of 2 theta over cosine squared theta plus 1 d theta. So odds are we might have to do things differently. That's okay. We don't mind. We don't mind. Let's see what we have. Let's start with the sine theta over cosine squared theta plus 1. Now, there's 8 integrals that you should know. Is this currently one of the 8 that we should know? I'll tell you the answer is no. When I talk about 8 integrals you should know x to a power, 1 over x, e to the x, sine, cosine, secant squared, secant tangent, and of course the best one is 1 over x squared plus 1, which becomes arctangent. So those are the 8 you should know. And if it doesn't look like one of those 8, what you need to do is start to say, well, what can I do to rewrite it? So algebra, trig, and substitution. Those are your 3 tools. Look to see how you can use those 3 tools. So algebra means look for ways to combine things, expand, factor, that type of idea. Trigonometry says look for possible trig identities. And substitution says, can I set one of the variables, are u equal to something, and get a nice du? So looking at the first integral, I can't help but notice I have a sine theta d theta upstairs. And downstairs, I have stuff in terms of cosine. Now, the reason I draw my attention to that is what's the derivative of cosine? It's negative sine. So this is very suggestive of making a substitution. So the fact that I see a sine here says, well, what if I set u equal cosine? So then that would say du would be negative sine theta d theta, but I don't have a negative. So I can do one of 2 things. I can introduce a negative upstairs, or what I like to do is I just like to move it around the constant downstairs. So here, what do we have? Well, if I carry it out on the first integral, what do I have? The sine theta d theta becomes a minus du. The minus can come out. And then I have cosine squared plus 1 becomes u squared plus 1. And is this one of the integrals that we know? Yes, it is. So this is minus arctangent of u. But what is u? Cosine theta. Remember, whenever you do a substitution, you got to go back and put in what you started with. Okay, so the first part, that turns out to be an arctangent. Well, maybe the second one will be an arctangent, because if it's one thing that I've learned from sitting in class, is that people in calculus love arctangent. Or at least some people really love arctangent. Okay, let's look at this one though. There's a little difference here. There's that 2. How big a difference can a 2 make in this problem? Well, what can you do with sine of 2 theta? Is there any identity that involves sine of 2 theta? Something where I have like an angle theta, and then I've like 2'd it. Maybe I guess we won't say 2'd it, we would probably say we like doubled it. So it's not like we've doubled our angle. So is there like a trig identity that involves a double angle? Maybe we could call it like a double angle trig identity. Is there any such thing? And the answer is, there is a thing. Sine 2 theta is 2 sine theta cosine theta. So it's good to know that one. There's 6 trig identities you should know. Sine squared plus cosine squared equals 1 is the most important one. Sine 2 theta shows up a lot. Sine 2 theta is 2 sine theta cosine theta. All right, so what do we do here? Well, one thing we can do is we can try our old substitution. I mean, it worked well the last time. Why not try it again? If it works once, it could work twice. Okay, so I still have the minus in front. I can still try it. So u equals cosine theta. Du minus du would still be sine theta, because it's still the same substitution, so same things. So what do I have now? I have the minus in front. Then I have the integral. Sine theta d theta. Oops, I forgot my d theta here. That's very embarrassing. Sine theta d theta. That becomes minus du. So now I have another minus, and I have a du. I still have u squared plus 1. Have I forgotten anything? I've forgotten the 2, and I forgot this cosine theta, so that's a u. All right, 2u over u squared plus 1. Is that on our list of things that we should know? And the answer is no. No. But wait a second. 2u and u squared plus 1. If I take the derivative of u squared plus 1, what do I get? 2u. Oh, wait a second. This is a nice situation where I have a function in the denominator and the derivative in the numerator. So this suggests making another substitution. Well, I've used u, so I'm going to double up. and say W, that is going to be u squared plus 1 dw would be 2u du. And I say, perfect. So this becomes the integral of 1 over w dw. Now, is that an integral we know? Yeah, what is it? It's natural log. Log, or ln, of w. Now, got to go backwards. W, u squared, plus 1. Okay? Still got to go backwards, because we've got to end up back in terms of theta. So u was cosine theta. Cosine squared theta plus 1. So now we can say our answer. We combine the two together. So our final answer is the following. I'll switch colors because it's our final answer. It's minus arctangent of cosine theta plus natural log cosine squared theta plus 1. And because I want all the points, plus c. Indefinite integral, put a plus c. Now, I will say some people were very enthusiastic about the plus c on the last exam, and they were like, everything gets a plus c, which is not true. You only need a plus c if you're doing an indefinite integral. If you're not, you don't need it. In fact, you might lose a point by putting a plus c where it doesn't belong. So use it at the right time, the right place. Okay. I think this one may actually be a quiz problem, which is okay. Quiz problems are actually pretty good. I mean, people are always like, can you give me more problems? And I'm like, you have so many problems. It's almost, the hardest thing is not that you don't have enough problems, it's, you have too many. I will say, and I think I've said this before, these problems are really good. I mean, they were chosen very deliberately. If you can do these, you're in good shape. Also, go back through the exams. If you go back through the exams and the practice exams, any problem which overlaps with what we have left for the final, those are also pretty good. Those are a really good set of problems to start with. If those are the only ones you look at, you'll be in pretty darn good shape. Excuse my language. I sometimes get a little bit salty when I get excited. But you have problems to work with. They're there. Number 6. We have the following function. H of x is e to the x over 4x squared plus 3. Determine the intervals when the function is increasing and decreasing. Well, when do I know if something is increasing? What am I looking for? First derivative. Right? Concavity, concave up, concave down, that's second derivative. Increasing, decreasing, that's first derivative. So, here we go. First derivative. H prime of x. What rule do I use? Quotient. So that says take the bottom, and then we're going to take that times the derivative of the top, minus the top, times the derivative of the bottom, and I'm going to divide that by the bottom term squared. Now the nice thing for us, 4x squared plus 3 is never 0, because everything is strictly positive. In fact, everything is at least 3 downstairs. So I don't have to worry about anything from downstairs. Upstairs, everything has an e to the x, so you can factor that out. So I have e to the x times 4x squared minus 8x plus 3 over 4x squared plus 3 squared. Well, what do we hope for? Best case scenario, what should happen? Best case scenario is things will factor. And I'll say that we've been pretty good about following that the whole semester, and we're not going to pull the rug out from underneath you. If something could possibly factor, it should factor. So if something is not factoring on the test, you should be like, let me go back and check my work, because I should be suspicious about this. Okay, so 4x squared minus 8x plus 3. Does it factor? And more importantly, how? Well, the 3 is not hard to figure out. It's going to be 3 and 1. Because of the minus, it would have to be minus and minus. And now, what's left? Well, the 4. It could be either 2 and 2, 4 and 1, or 1 and 4. And if you try it out, 2 and 2, Well, 2 would be minus 2 minus 6, first try, right out of the gate. Well, secretly, I kind of knew the answer. But you've got 2 hours. Plenty of time for you to get to your second or third if you need it. So now we start to say, okay, when could this be 0? And you might say, why do I care about when it's 0? I thought you wanted positive or negative. I want 0 because that's when things can change. So can e to the x ever be 0? No. No, e to the x can never be 0. I already mentioned the denominator will never be 0. There's no problems up there, or rather down there. 2x minus 3, can that be 0? Where? 3 halves. 2x minus 1, can that be 0? 1 half. So that says if I draw my number line, there are 2 potential places where I could switch signs. 1 half and 3 halves. And now that I know my places where I could switch signs, I just need to go through and test. So I test. So pick a number above 3 halves, like 1 billion. Or you could also pick 2. But the point is, it just needs to be above 3 halves. And if you plug it in, I like to do it down in the factored form. I already know the e to the x is positive. I already know the downstairs is positive. So let's say I'm going to get 4 minus 3, which is 1. 4 minus 1, which is 3. And it's positive. So first derivative is positive. So again, let me just emphasize this is first derivative, not the second derivative like what we were doing before. What's the number between 1 half and 3 halves? 1. Now, could you be creative? Yes. Should you be creative? No. Don't be creative. Choose simple values. Okay. Plug in 1. 2 minus 3, negative. 2 minus 1, positive. Net result? Negative. Okay, something below 1 half. 0. Okay, 0. Negative 3, negative 1. 2 negatives. 2 wrongs, make a right. All right. So now, remember, positive corresponds to increasing, negative to decreasing. So we can say that we are increasing in the following. If we are below 1 half and if we are above 3 halves. And we are decreasing in the following. If we are between 1 half and 3 halves. Now you might say, should these be less than or equal? And the answer is yes. And that either one will be fine. We will accept. It depends on the definition that you go by. I personally have the opinion it should be in equals, but other people disagree with me. And I like those people, so I will just close my eyes and silently tisk, tisk, tisk. But there we go. Okay. Number 7. Find the average value for the function f of y is 2y plus 4 sine of y over the interval between 0 and pi. Okay, so average value. Now we have a definition for average value. So in general, the average value between a and b is 1 over b minus a. So in other words, it's the length of the interval. Integral from a to b of f of t dt. So in our case, it's actually y. It doesn't matter, by the way, it's y. We can use any variable name we want. Variable names are just that. They're names. We can change names. We can give them nicknames if we needed to. All right, what is b and a in our case? Yeah, so b is pi and a is 0. So 1 over pi minus 0, integral 0 to pi of the function 2y plus 4 sine of y dy. So 1 over pi. What's the integral of 2y? Y squared. What's the integral of 4 sine of y? Yeah, this is one of those sine and cosine are a little tricky because, they sort of like swap which one has the sign change. So the integral of sine is minus 4 cosine. And now I'm going to evaluate from 0 to pi. Well, so that's 1 over pi. I have pi squared minus 4 times cosine of pi. Cosine of pi? Well, it's probably going to be either 0, 1, or negative 1. I'll narrow it down that much. Any thoughts about what it should be? It's negative 1. If you think about it, so thinking in a circle, cosine of pi, that pi is this direction, and the cosine is the x-coordinate. So I'm at negative 1. Okay, so that's, if I plug in pi, subtract 0 squared minus 4 times cosine of 0. Cosine of 0 is 1. Again, you can think about unit circle. 0 is this direction, so here's 0, here's pi. So cosine of 0 is positive 1. So if you look, minus minus makes this a plus. Here's another minus minus makes a plus. So we end up with pi squared plus 8 divided by pi. Now, what comes next? Yeah, you box it, we're done. We found the average value, and it said find the average value, and we're done. And you're probably saying, could a problem on the final be this easy? And the answer is possibly, yeah. I am optimistic that people are going to be like, sweet, I finished an hour early. Good. And it's okay if you do. It's okay if you do. All right. And it's okay if you take the whole 2 hours. You know, look, we're not asking you to do a speed race. Take your time. Time should not be an issue. This is not a test. We're testing for speed. We're just testing for knowledge. You have plenty of time. If you put in invested in learning the knowledge, you'll be okay. All right, number 8. Well, suppose you have the following function f of x. It's defined in terms of an integral. The integral from x to x squared minus 2 of the square root of 5 plus 11t squared dt. Determine the tangent lines at the points where y equals f of x crosses the x-axis. Now, this means that we have to find a couple things. So I have this function f of x. So the first thing is, could I find another way to write f of x? In other words, could I integrate the square root of 5 plus 11t squared? And the answer is, maybe if I took Calc 2. But it would not be pleasant. And we're not in Calc 2. So we're not going to do that. So we're going to instead do something even better than doing Calc 2, which is we're going to use the power of the mind. Let's think about this. We want to cross the x-axis. How do you know when you cross the x-axis? Y equals 0. So I'm interested in knowing when f of x is 0. Now, I don't have to sketch the f of x, but imagine for a second I sketch square root of 5 plus 11t squared. Is this ever negative? No. In fact, it turns out it's part of a hyperbola, but I don't need it to be precise. Let's think for a second about the question, when can the integral be 0? So, if I integrate from one location to another location, when can I get a 0 value? When's the only time I can get 0? The only time I can get 0, if the endpoints don't match, doesn't matter which order the endpoints are, but if the endpoints don't match, I'm getting area, which means that my function isn't 0. When the endpoints match, I get 0. So secretly, this was trying to nudge us to say, hey, look at these endpoints. These endpoints are going to give us away. So f of x equals 0 when x is equal to x squared minus 2. Because in those two places, I'm integrating from a value to the same value. And that's the only time it'll ever equal 0. Well, so that says that 0 equals x squared minus x minus 2. And based on our discussion that we just had a moment ago, what should be true? Should factor. So does this factor? And how does it factor? X minus 2 and plus 1. So, which two values of x do I care about? 2 and negative 1. Okay, so now I have this idea. I'm looking for the tangent lines at the following points, 2 and negative 1. But in fact, I can say it's 2 comma 0 and negative 1 comma 0. How do I know that these are zeros? Because I'm on the x-axis. The other thing is if I plug these in, they're set up so that the integral from, here would be negative 1 to negative 1 will be 0, and the integral from 2 to 2 will be 0. Okay. So now I have my points. What's next if I'm looking for tangent lines? Slopes. So, tangent lines, any line, but in particular tangent lines, slope and point. We have the point, got to find the slope. So, to find the slope, we're going to switch gears. So let's talk about f prime of x. So that's the derivative of the integral from x to x squared minus 2 square root of 5 plus 11 t squared dt. How do I go about taking such a derivative? Fundamental theorem. Fundamental theorem. And now this is a case where I have a function in both the numerator and the denominator. But that's okay. We have the technology. We can do this. So the rule says you start by taking the the top function, x squared minus 2, and plug it in anywhere where you see the t. So square root of 5 plus 11 x squared minus 2 squared. And now, so again, take the top function, plug in anywhere where you see a t, and then what happens? Chain rule, so you multiply by the derivative of the top function, 2x. Subtract, do the same thing, where you take this bottom function, and the subtract is the bottom. Everywhere you see t, you put in x. Square root 5 plus 11x squared times the function x, which is 1. So that's our derivative. So the last thing for us to do is to evaluate our derivative at 2 and at negative 1. So we cross our fingers and hope nice things happen. We're good people. We should have good things happen. 2 squared minus 2 is 4 minus 2, so it's 2. So this becomes 2 squared, which is 4. 5 plus 11 times 4. 5 plus 44. 5 plus 44 is 49. Square root of 49 is 7. I told you we're good people. Good things will happen. 2 times 2 is 4. Here we'll get 2 squared again, which is 4. It's not very surprising. 11 times 4 is 44. Plus 5 more makes 49. Square root of 49 is still 7. So subtract 7 times 1. So that becomes 28 minus 7, which is 21. So for 2, 0, it's going to be a slope of 21. Negative 1, 0. So negative 1. We're on the process again. I'm going to get 5 plus 11 times, well, it's going to be 1 minus 2 squared. 1 minus 2 is negative 1. Square that is positive 1. So it becomes 5 plus 11 on the inside. 5 plus 11 is 16. Square root of 16 is 4. Times that by 2 times minus 1, which is negative 2. Subtract. Run it again. Negative 1 squared is 1. So this becomes 5 plus 11, 16. Square root of 16 is 4 times 1. So negative 8 minus 4, negative 12. So the slope, negative 12. All right. So we're getting close. We've now found our points, and we've now found our slopes. So the last thing to do is to combine. So our tangent lines are y equals our slope, x minus our x value. Now you might say, well, wait, what about the y value? Well, it's y minus 0. So y minus 0 is just y. So y equals 21 times x minus 2, and then y is equal to negative 12 times x minus minus 1, or x plus 1. And those are the two tangent lines that we're after. Okay, that one's a fun one. I like that one. All right. Number 9. So let h of x be the function e to the 2x, a e to the x, plus a e to the x, plus b times x, where a and b are constants to be determined. Oh, this sounds like fun. We're going to find a and b. Well, how do we find a and b? Well, we're told that the function is decreasing only between 2 and 5. Find a and b. Okay, well, the fact that it uses the word decreasing, what information are we really being told about? First derivative. So it seems logical that when I'm answering part A, that I should start answering part A by looking at the derivative. H prime of x is the derivative of e to the 2x, 2e to the 2x, derivative of a e to the x, a e to the x, derivative of b times x, b. Now, we're told that the function is decreasing only between 2 and 5, which means it's increasing everywhere else. How are we going to take that information to solve for a and b? So basically, I know when it's positive, and I know when it's negative. So what else do I know? I know where it's 0. So where is the derivative of 0? 2 and 5. So I have that 0 is equal to h prime of 2. So that's 2e to the 4th plus a e to the 2 plus b. And that 0 is equal to h prime of 5, which is 2e to the 10th plus a e to the 5th plus b. So now what do we have? We have 2 equations, and we have 2 unknowns. 2 equations, 2 unknowns, that's enough equations and enough unknowns. It's a nice mix. So you need to solve for a and b. Now there's a couple ways to go about doing this. It's not unique. One way to solve for a and b is to say, let's solve for one of them. For instance, it's very easy to solve for b. In fact, it's really easy to solve for b in both of them. And then we can solve for a. Other thing is to do combinations. I can subtract and see what happens, for instance. So there's multiple ways to go about this. I'm kind of in a mood. I'm gonna subtract here. So let's take the first equation and subtract it from the second equation. And if we did that, we would get 0 equals 2e to the 10th minus 2e to the 4th, because 2e to the 10th minus 2e to the 4th, plus a times e to the 5th minus e squared. And the b's would cancel. So that's why I just did subtraction. This, by the way, is equivalent to solving for b and setting the 2 results equal to each other. So at this point, we can now do a little bit of rearrangement. So I could say, for instance, that a times e to the 5th minus e squared is equal to negative 2 e to the 10th minus e to the 4th. Or that a is equal to minus 2 times e to the 10th minus e to the 4th divided by e to the 5th minus e squared. Okay, in some sense we've solved for a. But you know, I like to go one step further. Let's solve for a even better. In other words, let's simplify. Now, normally if this was a test, I'd give a hint. That was a practice test. I didn't give a hint. I claim that we can simplify just a little bit more. Think about the relationship between e to the 5th and e to the 10th. How are they related to one another? So e to the 5th squared is e to the 10th. How about e squared and e to the 4th? It's also a square. So in fact, if you look at this, this is e to the 5th squared minus e squared squared divided by e to the 5th minus e squared. Whenever you see a difference of squares, what can you do? You can factor it. It becomes a sum of squares the sum, a plus b, a minus b. And now, you get cancellation. So that you can really clean it up. A is negative 2 times e to the 5th plus e squared. Okay, so that's a very clean A. Now, we're not done because we also have to solve for b. Well, but we have A. Once you have A, the b can't be hard. I hope not. Which one do you want to plug in for? First equation or second equation? A, first or second? Yeah, it doesn't matter, right? Because you'll get the same answer regardless. So we plug it into the first equation. So we're now solving for b. We're in our b mode. So 0 equals 2e to the 4th plus a, which is minus 2e to the 5th plus e squared times e squared plus b. Now, if you multiply this out, that becomes 2e to the 4th minus 2e to the 7th minus 2e to the 4th plus b. Now, where did these come from? Well, it's minus 2 multiplying through, but it's also e squared multiplying through. Notice something happens really nice. The e to the 4th terms cancel, and so b is equal to 2e to the 7th. So, we're now ready to answer part A. So A is minus 2 e to the 5th plus e squared, and b is 2e to the 7th. Okay, so that's the answer to part A. Now, we also have a second part. So, given the answer to what we just solved, find the point of inflection. Well, how do you find an inflection point? Second derivative. Okay, so let's look at second derivative. So I'm going to save that space here. H double prime of x. So I can actually just come here into this expression. What would that be? Well, the derivative of 2e to the 2x is 4e to the 2x. Then plus derivative of ae to the x, ae to the x. And derivative of plus b, 0. Now notice, here, e to the 2x, I can think of this as e to the x squared. And if I think of it that way, what I can do is I can actually factor out an e to the x. So it's e to the x, and then it's 4 e to the x plus a. So can e to the x ever be 0? No, e to the x can never be 0. I'm looking for an inflection point, and when I'm looking for an inflection point, what do? I look for where the second derivative is 0, which means I need to look for when this is 0. So the inflection point is going to happen when 4e to the x plus a is 0, or e to the x is negative a over 4, because I can subtract a divided by 4. Now I happen to know what a is. So I come here, I change the sign, so that's positive, that's a good sign. And then I divide by 4, so that's 1/2 e to the 5th plus e squared. Now, is this my point of inflection? And why is it not? It's e to the x, right. So I need to get not e to the x, I need to get x. So to finish the answer, to finally get what I want, what do? Take the natural log. So the answer for b is that x equals natural log of 1/2 e to the 5th plus e squared. So that's the answer for b. Now, you might say, can I simplify? And the answer is no. That plus is tough to do anything with. Logs do not like addition. They hate it. They hate it. There's nothing you can do. Multiplication, it's a field day. They love it. It's like they're running through a field of flowers and like, yay, look at all these multiplications. Woohoo! But man, addition, that's kryptonite to logs. Okay. So, here we go. Number 10. We're making pretty decent progress. Suppose that f of x is 2x cubed plus 5x plus 1. Find the value of the derivative of f inverse of x at x equals 8. Okay, so, this one is asking about the derivative of the inverse, so we should probably remember the rule. So here's the rule. The derivative of f inverse of x is 1 over f prime of f inverse of x. Okay, so that's simple enough. And so it's asking us for the value of the derivative at x equals 8. So what do we need? We need 1 over f prime of f inverse of 8. So that's what we need. I think the real point of this problem is just saying, do you remember how to take the derivative of the inverse? Oh yeah, because we knew it was on the test, so we made sure to memorize it. Let's go through, this is one of our fun onion problems, work through one layer at a time. F inverse of 8. So let's see what that would be. So I have this function, 2x cubed plus 5x plus 1. So when I'm talking about f inverse of 8, I'm not saying plug 8 into the function. What I'm saying is I want to get 8 out of the function. So which value of x, when I choose x to be a certain value, gives me 8? Now, in case you're wondering, is it okay to guess? The answer is yes. Guessing is actually a pretty good tool in mathematics. We make it sound like it's a terrible thing, like you should never guess, but really, guessing is great. Do you see a nice choice for x? Yeah, 1, because 2 plus 5 plus 1 equals 8. And we see that, we can even say, x equals 1 works. So we have that f inverse of 8 is 1. So now we know that this is 1 over f prime of 1. Good, good. So next thing is I have to find f prime. So let's figure out what f prime is. F prime of x, well, let's work it out. Derivative of 2x cubed, 6x squared. Derivative of 5x, 5. Derivative of plus 1, 0. Don't need to write down the 0. So plug in 1, what do you get? You get 11, because it's 6 times 1 plus 5. So we plug that in here, so you get 1 over 11. And now what happens? You box it, and you're done. Good. So this one is testing, do you know your definitions? And you should. You should. Okay. Number 11. We are given the following. The line y equals 5 minus 2x is tangent to y equals f of x at x equals 1. The line y equals 3x minus 4 is tangent to y equals g of x at x equals 2. And the point 2, 1 is on this curve, f of y squared plus g of x squared equals 4xy plus d. And there's two parts again. Part A, what is d? And part B, what's the tangent line to the curve at the point 2, 1? Okay, so let's think a little bit about what we're being tested on here. First off, this expression, f of y squared plus g of x squared equals 4xy plus d, what is that? What name do we have attached to that? I'm sorry, I feel like I'm not asking the question very explicitly here. So what's another way I could phrase this? It's not explicit. It's implicit. It's implicit. Where we have a relationship between x and y, but there's no way we could solve for x and y. We just don't have enough information. I can't solve for y equals. I can't solve for x equals. So this is a question about implicit differentiation. That's okay. That's all right. But it's really a question that's about a couple of things. So there's going to be implicit coming up. But the other thing is it's talking about tangent lines. See, we don't know what f and g are. What we do know is just a little tiny bit of information about f and g. So let's talk about the little tiny bits of information that we know. So for f of x, what do we know about f of x? Well, we know that the line y equals 5 minus 2x is tangent at 1. Tangent line stores two pieces of information: the value of the function, the value of the derivative. So I claim we know what f of 1 is, and we know what f prime of 1 is. What is f of 1? It's 3. And how do we know it? You take x equals 1 and you plug it into the line. The tangent line evaluated at the point matches with whatever the function does. What's f prime of 1? Negative 2. And how do we know that? It's the slope. The slope of the line gives us the value of the derivative. Now, for g of x, again, we don't have a lot of information, but we do have some. And in this case, it's at 2. So we should be able to say something about g of 2 and g prime of 2. What is true about g of 2? So plug 2 into here, and we get 2. 6 minus 4. G prime of 2? 3. Because we see it has slope 3. So what they did is they said, oh, we're going to obfuscate information about the function by putting it into the tangent line. But by this point in the semester, we're good. They can't over-obfuscate. We know their tools. We know their techniques. And we're not going to miss that. All right, so let's start by answering part A. So for part A, I come in here and I say, well, 2 comma 1 is on this curve. So that says that f of 1 squared plus g of 2 squared equals 4 times 2 times 1 plus d. And what I did here is I put in x equals 2 and y equals 1. So f of 1 is 3. So 3 squared is 9. G of 2 is 2, so that's 2 squared is 4, is equal to 8 plus d. 9 plus 4 is 13. So 13 equals 8 plus d. So finally, we subtract a from both sides, and what do we conclude about d? It's 5. So the answer for what's the constant for d, it is 5. Okay, so that wasn't so bad. Now it says find the tangent line to the curve at the point 2, 1. In fact, in some sense, we're halfway done, because we already know the point. The point is 2 comma 1. Now what we don't know yet is the slope. And that's why we talked about implicit differentiation earlier. We anticipated we would need it. And here's when we need it. So we're going to go through and take the implicit derivative of both sides. Remember, think of y as a function of x. So whenever you reach that point, plug in y prime. So when you get to the point of talking derivative of y. So derivative of f of y squared, chain rule. The 2 comes down, f of y to the first power, times the derivative of f of y, which is f prime of y, times the derivative of what's on the inside of f of y, which is derivative of y, also known as dy dx or y prime. Both are acceptable. Okay, coming to the next term, g of x squared. Okay, the 2 comes down to g of x to the first times g prime of x, because we're doing the chain rule, times 1. So if we were to keep going all the way down, we can say what's the derivative of the inside? In this case, the derivative of the inside is 1. All right, equals, and I did not plan well. Okay, 4xy, going to use the product rule. The derivative of 4x, 4 times y, plus 4x times the derivative of y, which is y prime. And then the derivative of d, the derivative of d is 0. Derivative of a constant is 0. So that's it in general. And now we plug in what we know. What do we know? Well, we're at 2 comma 1. And so what we're going to do is everywhere I see a y, I'm going to put a 1. And everywhere I see an x, I'm going to put a 2. Okay, so 2 times f of 1 times f prime of 1 times y prime plus 2 g of 2 g prime of 2 is equal to 4 times 1, which is 4 plus 8 y prime. All right. So f of 1 is up here. It's 3. F prime of 1 is negative 2. So I have 2 times 3 times negative 2. So that's going to give me negative 12 y prime. G of 2 is 2. G prime of 2 is 3. So this is going to be plus 12 is equal to 4 plus 8y prime. Now, we're out of space on this right-hand side, so I'll just move to the left-hand side. Move the terms across. Everything with y prime on one side, everything that's not has a y prime on the other side. And so you're going to get that 20y prime is equal to 8. Our y prime is equal to 8 over 20, but we can clean that up. Top and bottom are both divisible by 4, so that's 2 over 5, 2/5. So that is my slope. Now I have my slope. I already had my point. If I combine the two together, I get my line. So my line is y minus the y value, which is 1, y minus 1, is equal to the slope, 2/5, times x minus my x value, which is 2, x minus 2. And that is a great way to leave our answer. And we're done. Good, good. Okay. How are you doing? It's been a while. Checking in? Hanging in there? We're doing pretty good. We're at a good pace. We'll finish with plenty of time. Okay. Here we go. Number 12. So find the value of a, which is positive, so that the average value of the function f of x equals 30x minus 4x cubed between 0 and a is maximal. What kind of problem are we in? Optimization problem, yeah. When you see that word maximal or minimal or anything that says find the biggest, find the smallest, anything like that, you're in an optimization problem. All right, so we're trying to optimize. What is it we're trying to optimize? Well, we're trying to optimize average value because it says we want to make the average value maximal. So what we need to do is start figuring out what is the average value. So we're between 0 and a, and we have our function. So to find the average value, we can have that the average value, I'll just call it capital F for now. Capital F for given a. Average value for given a. So that's 1 over a minus 0, and that's coming from these endpoints. Integral 0 to a of the function 30x minus 4x cubed dx. So that's 1 over a. What's the integral of 30x? 15x squared. What's the integral of 4x cubed? X to the 4th. Okay, evaluate from 0 to a. So if I plug in 0, I get 0, which is nice. So I'm going to plug in a. I'll get 15a squared minus a to the 4th. And notice everything has an a, so I can divide. So this becomes 15a minus a cubed. So that's the average value given a particular a. You give me an a, that's what the average value over the interval between 0 and a is. Now we're trying to optimize this, in particular we're trying to maximize this. So the first thing we've done is we said, let us express our thing we're trying to maximize as a function. So we've done that. What comes next? Take a derivative, because once you have your thing you're trying to optimize, you take a derivative. So f prime of a, so use the last term, that's the easiest, is what? Yeah, 15 minus 3a squared. Okay, you've taken your derivative, what comes next? Yeah, set it equal to 0 and solve. 3a squared equals 15. A squared equals 5. A equals square root of 5. Now you say, wait a second, what about plus minus? I don't need to worry about it because a is positive. Now sometimes you might be in a situation where you're like building a silo or something, and then you say, well, how do I know it's plus minus that I can throw away the minus there? If you have something relating to a physical quantity, it's always the plus. You know, you can't have something of a negative length. All right, just things to keep in mind. Okay, well that one wasn't bad. Now this test is going to be fun. It's a shame we can't have like a longer test. Oh well. All right. Well, I spoke too soon. Number 13. Ugh. All right. Given the following table. Okay, so this test, can you read the information from a table and use it? So I have this big table, and I want to take a derivative, f of g of x plus g of f of x divided by f of x plus g of x, evaluated at x equals 2. This problem is almost a pure raw, do you know the rules? And sometimes the answer is yes, and sometimes it's like, I'm not sure. So, be patient. Don't feel the need to rush. Make sure you know which rule you're at. So let's look at this expression. What's the first primary rule, the big overarching rule that comes into play initially? The quotient rule. Okay, so we're just going to be very patient here and work our way through taking this derivative. So I have f of g of x plus g of f of x over f of x plus g of x. Okay, so the quotient rule says you take the bottom, and then you times that by the derivative of the top. Okay, so now we're taking the derivative of the top. What rule is going to come into play when I take these derivatives? The chain rule. So what's the derivative of f of g of x? Where does it start? F prime of g of x, and then g prime of x, plus g prime of f of x times f prime of x. Okay, bottom times root of the top minus the top, f of g of x plus g of f of x times root of the bottom, which is f prime of x plus g prime of x. Okay, and all that divided by the bottom term squared. Okay, so that's the derivative. That's actually the hard part of the problem. Now is the tedious part of the problem, because you'll see it didn't just say find the derivative. There was this bar here. This bar says evaluate. So we're going to take our derivative and we're about to evaluate at a particular point, the point 2. So to do that, we're just going to patiently work through the pieces. So everywhere I see an x, I'm going to have a 2. So that is f of 2 plus g of 2, f prime of g of 2, g prime of 2, plus g prime of f of 2, f prime of 2, minus f of g of 2, plus g of f of 2, times f prime of 2 plus g prime of 2, all that divided by f of 2 plus g of 2 squared. And at this point, we're just going to go through and start reading off our table. Okay, f of 2 is 1. Okay, so we've used this entry. F of 2 is 1. G of 2, 3. 1 plus 3. Now, for the next one, g of 2, we've said is 3. What is f prime of 3? It's 1, because I can read it here. So that's 1 times g prime of 2. G prime of 2 is 2. Plus f of 2, we said was 1. So what is g prime of 1? G prime of 1 is also 1. Oh, it's very good. Lots of 1s here. And f prime of 2? F prime of 2 is 4. Okay, good. So there we got g prime of 2, f prime of 2, minus f of g of 2. Well, g of 2, we said was 3. F of, let's see, did I have this right? Yeah. F of 3 is what? It's 4. So I have 4 plus g of f of 2. Well, f of 2 is 1, and g of 1 is it's also 4. So plus 4. Then f prime of 2 is 4, and g prime of 2 is 2. All that divided by f of 2 plus g of 2, which is 1 plus 3 squared. Okay, so this becomes 4, 1 plus 3, then it's 2 plus 4 times 6 minus 8 times 6 all over 16. 4 times 6 is 24. 8 times 6, 48. 24 minus 48 is negative 24 over 16. Divide top and bottom by 8. Negative 3 over 2. Okay. We survived it. Now, you might say, wait a second, we didn't use most of this table. Is that a problem? No. Oftentimes when they give you a table, you should expect you're not going to use all of it. And part of it, what we're testing on is, do you understand what the right things to grab are? Okay. Well, that one was the not fun one. But that's okay. That means we must be into just only fun problems left. Number 14. This is a little bit wordy. Usually the longer a problem is, the easier it is to solve it. Suppose the weight of a cloud in tons after t hours, denoted W of t, decreases proportionally to its surface area, and that this process speeds up over time until the cloud is completely gone. Now, we can approximate this behavior with the differential equation. And it even gives us the differential equation. We don't even have to guess. W prime is negative 5/3 times t, w to the 2/3. All right? Given that the cloud initially weighs 1,000 tons, how many hours until the cloud is completely gone? Now we have to figure out this information. Initially weighs, okay, imagine I could spell. Initially weighs. Initially weighs 1,000 tons. What does this mean? So initially, times 0, we are 1,000. How many hours until the cloud is completely gone? What am I looking for? So what should my, let's phrase it this way. What kind of thing is my answer? Is my answer going to be a function? No, it's not a function, because it's not asking for a function. It's asking for how many hours. So the answer should be a number. So we're looking for a number. Well, we want the cloud to be completely gone. When is something completely gone? When it's 0. So we want to know, when does W of t equal 0? Now, knowing this information ahead of time can help us speed up the process of solving it. Okay, so it's good to understand what we're looking for. It's always good to know where. In fact, I would say 100% of the time, make sure you know what you're looking for before you start looking. Because otherwise you might miss it. Now, what technique is this? Or what general type of problem is this? It's a differential equation problem. How do we know it's a differential equation problem? Well, they pretty much told it. That was a pretty good clue, that it was a differential equation. The other thing that gives it away, though, is the fact that I see W prime on one side and W on the other side. This is something which mixes the derivative with the original function. So, we go back to where we were back on problem 1. Way back then, we were so innocent back then. So dWtt is negative 5/3 t and w to the 2/3. So do you remember how we did it? Step 1, separate. So dw divided by w to the 2/3 is equal to minus 5/3 t dt. Okay, we've separated. What comes next? We integrate it. Now, by the way, w to the 2/3, because we're in calculus, we'd write that as w to the negative 2/3 dw. The only thing we leave something downstairs if it's like dw over w, because that's something that's setting us up for a log. If it's not a log, it's easier to think of it as w to a power. Okay, so we're now integrating. All right, the integral of w to the negative 2/3 dw. Well, add 1 to the exponent. Negative 2/3 plus 1? 1/3. And then we're going to multiply by the reciprocal, so that becomes 3w to the 1/3 equals antiderivative of negative 5/3 t dt. Well, negative 5/6 t squared. And then plus c. All right, at this point, let's solve for c. Okay, so how do we solve for c? Well, we put in when t equals 0. Where am I at? Oh, I wrote it over here. There we go. Here's where we solve for c. When t equals 0, we should have 1,000 for w. What's the cubed root of 1,000? That's 10. It's almost like they deliberately chose a number we could work with, because they did. So 10 times 3 is 30. Negative 5/6 times 0 squared is 0 plus c. So what is c? c is 30. Now, we have two choices. We can now either do the problem the long way, or we can jump almost right to the answer. We're going to jump right to the answer. Because remember, do we need to have w? We actually don't have to have w, because our answer, it doesn't ask us for what w is. It asks us for when does w of t equal 0. So here's how we're going to do it. W of t equals 0, we're going to come back to our relationship. So we have 3w to the 1/3 is equal to negative 5/6 t squared plus 30. And we're going to set w equal to 0, because we want to know when it equals 0. Okay, so that's going to equal 0 when negative 5/6 t squared plus 30 equals 0. Or 5/6 t squared better be equal to 30. Or t squared, well, I'm going to divide by 5, and that's going to give me 6. And multiply by 6 gives me 36. And so that's when t squared equals 36. So what is t? T will be 6. And our units are hours. 6 hours. And how do I know it's hours? Because it told us 6 t hours. And we're done. That's it. Okay. Well, 2 to go. Find values a and b so that the following function is continuous at x equals 0 and x equals 1. You might remember a problem similar to this on the first exam. Here's our chance at redemption. Maybe this time we'll get it. Or at least we'll get more than an average of 2 points. Okay. Well, we've gained something since the first exam. What's our tool that we have now? L'Hôpital. Now you might say, why are you saying L'Hôpital? I don't see any limit involved. Well, this goes back to our definition of continuity. So if I want to be continuous, what needs to happen is I really need to have the limit exist. So remember the definition of continuity. So continuity says that the limit as x approaches a of f of x is equal to f of a. That's the definition of continuity. Now here, because of the way it's set up, the ax plus b, I'm actually matching 0 and 1, so that's not really hard. But what I really need to be doing here, because it's piecewise, is I need to look at my pieces. So in particular, I'm going to do the following. So we're going to do 2 rounds. Let's do the 0 here. So round number 1. So I'm going to take a look at the limit as x approaches 0 from above, and of f of well, not f of x, g of x. When I approach 0 from above, I look like ax plus b. On a side note, what does ax plus b approach as x goes to 0? It approaches b. Now, that was easy. These problems seem so much simpler. Well, that better be equal to the limit as x approaches 0 from below. If I'm below 0, I look like x squared plus 2 log cosine x divided by x to the 4th. Well, what does that do? It goes to 0 over 0. Cosine of 0 is 1. Log of 1 is 0. 0 squared is 0. 0 to the 4th is 0. So this is going to 0 over 0. Oh! What can we do? L'hôpital! Are we allowed? Yes. If the problem does not explicitly forbid it, and no problem on this test explicitly forbids a technique. So you're allowed to use it. So, l'hôpital, mon ami, we'll meet again. Okay, so limit x approaches 0 from below. Well, take the derivative of the top and bottom. Derivative of x to the 4th, 4x cubed. Derivative of x squared, 2x. Derivative of 2 log cosine x. Okay, so log cosine. So log of something is 1 over something, so that's 1 over cosine, times the derivative of cosine, which is negative sine. So it's negative sine over cosine, also known as tangent. So this becomes 2x minus 2 tangent x. Okay, what does that go to? 0 over 0. So what do we do? L'hôpital! Okay, limit as x goes to 0 from below. Okay, derivative. Derivative of 2x? 2. Derivative of 2 tangent x? Secant squared x. Divided by derivative of 4x cubed? 12x squared. What does that go to? Well, downstairs goes to 0. That's easy. What is secant of 0? It's 1. So it goes to 2 minus 2, which is 0. What do we do? L'hôpital! Oh, l'hôpital! Ah, my friend. Okay, upstairs. The 2 goes away. All right, minus 2, derivative of secant squared. Okay, so that'd be 2. Then I bring the chain rule. 2 comes down. Secant x times the derivative of secant, which is secant x tangent x. Over, what happens downstairs? 24x. Well, what does this go to? 0 over 0. Yes! Yes, again! My goodness, this is fantastic. This is so much easier, though, than when we did this before, because we were like, oh my gosh, I got to use some crazy trick identity. And now it's just like, no, derivatives, they're totally awesome. Actually, let's not do l'hôpital yet. Let's clean it up before we take l'hôpital. So that's minus 4 secant. I'm not taking l'hôpital, I'm just rewriting it over 24x. Now, you could actually get away without doing l'hôpital, but no, I like to say, l'hôpital. No, you don't actually have to make the noise, by the way, to do the rule. If you're wondering, if I don't do the noise, will it be correct? No. It helps me. It helps me. Okay, so we go through. All right, minus 4 derivative secant squared x, 2 secant x to the 1 times derivative of secant is secant x tangent x, then minus 4 secant squared x. Oh my gosh, I'm going to run out of space. Ran out of space times the derivative of tangent, which is secant squared x, all divided by 24. Now, at this stage, what do we say? Game over. we know we're no longer going to be using L'Hopital. Why not? There's not a 0 downstairs. There's no chance for a 0 downstairs. Whatever happens is what happens. So what happens? Well, the first term has a tangent, which means that's going to go to 0. The second term has a whole bunch of secants times -4. So we get -4 on the top, 24 on the bottom, -1/6. What is this? That's B. We just found B. We're halfway. Okay, so there we go. There's B. Now, let's do the second half. How do we find the second half? Same thing, but at 1. Okay, so we're going to look at the limit as x approaches 1 from below of the function. Well, that's ax plus b. Well, that's going to be easy to find. That's going to be a plus b. But I know what b is, so that's a minus 1/6. So this is because I know b equals 1/6. That better be equal to the limit as I approach 1 from above of my function, which is x plus 3 squared minus 16 divided by x times x plus 4 minus 5. Now, what is this limit doing? Well, where does it go to? On the top, plug in 1. 4 becomes 4 squared minus 16, which is 0. Bottom becomes 1 times 5 minus 5, which is 0. Goes to 0 over 0. Now, if you want, and you're like, I cannot take another, we can do the whole thing that's left. We can finish it up without ever doing L'Hopital. Or we can do L'Hopital. I don't know how you feel. Maybe I'll show you how to do it without doing L'Hopital, just because it's a good walk down memory lane. So, I know, I feel the same way. Upstairs, x squared plus 6x plus 9 minus 16 is minus 7. Downstairs, it's x squared plus 4x minus 5. But really, if you stare at this for not very long, you say, wait a second, that's x minus 1 times x plus 7 over x minus 1 times x plus 5. And what happens is that the x minus 1's cancel, and they say, oh, well, plug in 1. 8 over 6. So you can still do limits without L'Hopital. Don't feel like every limit in the future that you ever have to see is like, okay, let me pull out L'Hopital. Sometimes you don't have to. Now, that is not A, but it's close. How do I get A? Add a 6. So A would equal 9 over 6, also known as 3 over 2. So we'll put our final answer here in a box. A equals 3 over 2. B equals minus 1 over 6. Okay, good times. Which brings us to our last problem. So, due to your hard work in your job on Moon 13, you have been promoted to management. On your first day, you have been tasked with setting the production levels for a new product line called ZAMPs. You see that the cost of producing Z ZAMPs is 25 plus Z, and that the market forecast report predicts that the revenue for Z ZAMPs is 21 arctangent of Z plus 4 log of 1 plus Z squared. I suspect someone in marketing must have taken my class if they have an arctangent, but that's okay. So, how many ZAMPs should be made to maximize profit? Now, what kind of problem are we in? Optimization, because we see the word maximize, and we're trying to maximize. Trying to maximize profit. Now notice that the word profit only ever shows up once. So we have to figure out what profit is. So this takes us back to our Econ 101. Okay, so how do you compute profit? Profit is revenue minus cost. So profit, that's our revenue, 21 arctangent of Z, plus 4 log 1 plus Z squared, minus cost, 25 plus Z. Okay, so there's our function. That's what we're trying to optimize. So what do we do to optimize it? Take derivatives. Derivative of 21 times arctangent of z. Well, 21 is 21. Derivative of arctangent is something we probably all know by now. 1 over 1 plus z squared. Okay, how about 4 natural log of 1 plus z squared? What's that derivative? So whenever we see a log, just whatever's on the inside goes downstairs. What goes upstairs? The derivative, so 2z. So 4 times 2z over 1 plus z squared. Okay, so be careful here with this minus. Remember that this minus goes through. So it's minus 25, derivative of minus 25, 0. And minus z, derivative of minus z, negative 1. Okay, so at this point, this is the derivative of profit. Well, let's clean this up. Putting our algebra hats on, what should we do? Combine them. So we need common denominator, which is why it's really nice that both things are 1 plus z squared. So this becomes 21 plus 8z, then minus 1 plus z squared, all over 1 plus z squared. Also written as minus z squared plus 8z plus 20. Let's see, am I doing that right? That looks right. All over 1 plus z squared. Now, because we're in our class, we strongly believe that most things should be nice. In particular, what should be true about polynomials? They should factor. Does this factor? Let's hope it does, because I've written it down like it does. What does it factor as? Z minus 10 and Z plus 2. You can always check. If you just plug 10 in, minus 100 plus 80 plus 20 is in fact 0. Okay, so again, you should always look for factoring. If something's not factoring, either you need to look harder or you've made a mistake. Okay, now all this, of course, is sort of secondary. What really needs to happen with our profit function? What do we do? The derivative of our profit function, what do we do? Set it equal to 0. So when do we get a 0 out? Well, the denominator doesn't do anything. Z plus 2 would be 0 at negative 2, but we can't unmake negative 2 zamps. Well, maybe if we go to our competitors and start disassembling. But that seems unfair. We're ethical mathematicians. So what does that leave us with? 10. Which means there's only one viable answer. And right now, because we took off the verifying parts, so you're only going to get one viable answer. That's the answer. So 10 zamps. Done. That was it. We finished all 16 problems in under 2 hours. You only have to do 7 problems, and you get the full 2 hours. Plenty of time.